Now that we have the design in additive form, let's go back and show how the design was made using topology optimization. So we're going to roll the model back to show all the information that we used to make this topology optimization. So here's all of our important parts. They were wavelengthed from the original geometry to create this new piece of geometry, and we have everything in place, so we're going to give it some inputs. So if we go to our topology optimization, these are our tools for creating an optimized part. I guess the first thing we'll do is we'll assign a material. And you can see the materials ABS. So we're happy with that. We're going to assign ABS to our design space. Now what is the design space? The design space is the space that the design must stay within. It cannot go outside of that space. So this is our design space that we associated to the original model and used synchronous technology to create a design space for us. So with our design space, then we could talk about managing design constraints. So we have a lot of design constraints that we could do within NX. For instance, we could do plane of symmetry for symmetrical designs. We could even do symmetry of symmetry, rotational symmetry, extrude along a vector. Perhaps we're going to use conventional tooling, but we want to take advantage of topology optimization, but we know eventually it's going to be plastic injection molded or machined. So we can do that. We can even add draft and parting lines. And then for 3D printing, we can void fills so that we have no internal cavities. We can control material spreading. As we showed in the previous video, we can control how much that material spreads depending on our process. Overhang prevention so that we don't have, if we're printing and we're using a printer that requires supports, we don't have supports that are within the part itself, that making it very difficult to clean up. And self-supporting to try to alleviate having supports at all, to make the part in a fashion that does not really require supports. So what we have here is, I believe we have material spreading. We're going to turn that off for right now. If I look through, maybe what we will do is we will just tell it we want this part to be self-supporting, and we'll add that. We're just going to add one constraint, and we're going to make it self-supporting in this direction, and we're happy. So that's good. So self-supporting. And then we will manage our optimization features. So the first one we have is a copy face. That copy face is important because it has to match the existing design. We're working in context of the design. And we want it to be 3 millimeters thick. So that's the copy face. And then we want to this extrude to be a feature, and we're going to shell that, so there will be material around it. That way we can control the material. If we said just keep out, it may give us nothing in that area, which is exactly what we told it. But we want a hole with material around it. And that's going to be fixed. Something must be fixed. And then the airflow that we designed using synchronous technology is going to be another shell with a thickness of 2 millimeters around it. And there'll be no constraints on that. So this is fixed. This has no constraints, and this is our design space. So we'll hit OK. Now, you have to have loads. In order for the optimization to work, there has to be a load. There'll be no load on the copy face, although there could be. Something needs to be fixed, and this is the fixed part. And this body here is going to have a force of 10 newtons, and it'll be in the direction of this arrow. We really don't care about force for this design, but in most designs, force is extremely important, but you do have to apply some force. So we're going to accept that, and we have all of our inputs, so we'll just simply accept them. Now what we can do is we can run our optimizer. So we're going to run the optimization, and we can optimize for mass, which is weight. As a designer, that makes perfect sense to me. You can do safety factor or mass target. We're going to do, natural frequency is the last one. We're going to do for mass. And you could do the global resolution, which is number of facets. We're going to set this over here to the left. You will still get a very, very good design. And then as we refine our design, we could include more facets. It'll take longer, but it'll be more refined design. And then if we select our design space, we can estimate our optimization parameters. And when I hit that button, it gives us a number down here. And basically it's the design space minus the keep outs and plus the keep ins and the shells and everything. It gives us like a high and a low. And it gives us something roughly in the middle. And then we can manipulate this number to reduce the mass and give us possibly a better design, or we can increase it to give us a more beefy mass and improve our design that way possibly. So we're just going to leave it as is, and we're going to run this design. So now it's currently running, and it gives us a bit of information. It'll tell us, things, standardized type information. But up here, it's actually running. And as it runs, it's going to start finding information, and it's going to give us outputs like you might want to increase your resolution. You might want to reduce your force. There's things you could do to improve it. If it's flatlining, it's struggling. A little bit of flatlining is okay, but a lot, it's probably going through some narrow corridors and it's struggling a little bit. Doesn't mean it won't work, doesn't mean it won't be a good design, but flatlining, you want to avoid having too much. But that looks like a good calculation. Everything's going good. And it finished the first calculation, so now it does a second calculation. It always goes through twice, and then once it's done, it will give you the output. And if it fails, or if there's a problem, it will tell you why it has a problem, and then you can go improve that situation. So a problem would be too little mass, too much force. So either more mass or less force. Okay, so now it says the recipe is finished, and everything seems to be good. The status is it's meshing. Behind the scenes, it creates a mesh, which is our part that we can use if we choose to do so, if we're happy with it as a convergent body. And then we can continue the design to finish the design using conventional modeling techniques. And then we can evaluate the design, make sure it's a good design, optimize it for printing, and place it in the printer. Okay, the design is finished, and you can see it in the background. There it is. It looks like it's done kind of a good job. So if we take a look at it, let's get rid of some of our construction input geometry. Okay, our design is finished. So this is the part that it made for us. We might have some improvements. We could possibly improve the model a little bit there, I see. It's a possible thing, but with convergent modeling we can do these things. It actually looks like it's done a pretty good job. It's kept the face, which is so important to the design and context, and it's kept all the important characteristics of the inputs that we care about. But I, as a designer, and something I've never had in my 30-some year career, is now I could look at things like I could look at displacement. I could see the quality of the model. For years I've just gone on best judgment because being a designer, I designed, and the analysis department would tell me where improvements could be. And red doesn't necessarily mean bad, but red is areas of concern that I could possibly improve the model. In this case, I don't think that there's anything like that. Blue is potential cost savings. The model is pretty beefy. It's areas that we could thin it out, use less material, and potentially save money. So that's something that we could do as a designer using this tool. Stress. Now stress, I could see where if there really was stress on this part, it's not a part with high loads of stress, but if there was, and I could see the red areas, I could do things like put blends in those areas or increase the blend so that I could reduce the stress and I could make a better part. So these are things that I could do as a designer to improve the quality of my model. Now, I like this part. I'm happy with it, so I'm going to look at it. This is the part that we would actually build. And what we're going to do is, being that we're happy with it, we'll go to convergent modeling. And with convergent modeling, I'm going to convert this. I'm going to put automatic cleanup on and clean up some of these edges and improve it even a little more. And I'm going to create a convergent body. And by having this convergent body, this is a part that we can actually manufacture now. And this is the part that we can actually use conventional modeling techniques with to improve the design. So there it is. There's my convergent body. And I'm, this is one of my designs I could take to my design review. And we could look at it. And I could compare it to some of the past runs that I've done to see what is the real one, what's the best one that we're going to use. We could kind of go through all the different design scenarios and see. And then once we get to the ideal part, perhaps it's this one, and maybe it's the one that we just did, then we can finish our design. So we use topology optimization to make this part, referencing the original parts with the optimizer, and we showed that you could run it and get several different results.